Around the age of 15, I joined a group called the Society for Creative Anachronism, also known as the SCA. The organization is sort of like a Civil War reenactment group, but instead of focusing on reenactments of actual battles in a civil war, the SCA covers the arts, sciences, and culture of a broad time span pre-17th century. This is mostly focused on the Middle Ages in Western Europe. The members gather at events to recreate the Middle Ages as they ought to have been. There is no LARPing here. While there is much more to the organization, the most visual parts of the SCA to an outsider are the one-on-one combats and the wars. Wars occur between baronies, principalities, and kingdoms on a regular basis. The annual Pennsic War, which you're viewing here, is one of the largest, and it traditionally occurs during August in Slippery Rock, Pennsylvania. This 2-week event features a full-out war between the Kingdom of the East and the Kingdom of the Middle. This war is enormous since both warring kingdoms bribe other kingdoms to join in on the fun. These clashes are brutal, and while safety is of utmost importance, these are non-choreographed real combats. The only things that are not real on that battlefield are the weapons. Instead of actual swords, pikes, arrows, and the like, weapons are typically crafted from rattan. I can attest from experience, you still swing these weapons with significant and, if unarmored, deadly force. These combatants are trained and hit with emphasis. So what does this all have to do with math? Well, the trajectory of a missile fired in combat is generally parabolic, so in this video, we're going to be using quadratics to help lay siege on a castle. So let's get medieval.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this capstone video, we will use all our prerequisite skills with quadratics from algebra to help wipe out our opponent's forces who are hiding behind those castle walls on the battlefield. So, dust off your long swords, polish your armor, grab a turkey leg or a tofurkey leg if need be, and prepare for battle. The following is very important to understand. As this is a capstone video, I will not actually review anything. Instead, you will see my handiwork as I mention the prerequisites being covered, but you should already know this material well enough to do this without my help. There'll be links to the prerequisite topics listed in the description below this video, so if you struggle following my logic, or if you feel as though you could not perform a specific step without some assistance, then you can see the relevant prerequisite link for help. The name of the game here is to squeeze as much mathematical knowledge as possible out of the problems I present. On to the example. The Pennsic War is coming up, and we need to help the design team who are building a catapult. Our job is to develop the mathematical model of the path of the projectile being fired from the catapult. Suppose the catapult is to be placed 500 feet from the castle wall. Let d be the horizontal distance that the projectile travels after being fired from the catapult, and h be its height during flight. Hopefully the path of the projectile looks something like this. If the path of the projectile is given by h of d, which is equal to negative d squared plus 400d, how far away from the catapult will the projectile be when it hits the ground? Go ahead and pause this video to answer that question and to sketch a path of travel for the projectile. This question covers two prerequisite skills. First, you need to be able to interpret what hitting the ground means mathematically in terms of our function. In this case, it means we need to solve h of d is equal to 0. Second, you need to solve this resulting equation. It requires the ability to factor out the greatest common factor and then knowledge of the zero factor principle. In this case, we see that the projectile hits the ground when either d is equal to 0 or d is equal to 400. Transforming from mathematics back to language, this means that the projectile is on the ground when it is 0 feet from the catapult and 400 feet from the catapult.
Time for a reality check.
Do you see a problem with this? but let's engage a few more prerequisite skills to analyze the issue here by graphing. First, we know that the original function for the path of travel is a quadratic, so the path of its solution set is a parabola. Second, since the lead coefficient is negative, our parabola should open downward, so it should have this basic look. Note that I am not doing an accurate or clean graph here, this is just a sketch. Third, we know that the zeros of a quadratic occur when the graph strikes the horizontal axis. Using all this information, we can get a somewhat accurate sketch of the graph. Again, note I am not concerned right now about the value of the vertex because I'm more anxious about these horizontal intercepts. The reason why? They're wrong. Not from a mathematical perspective, we did everything fine computationally, but from a realistic and effective perspective. We can easily see that our function says we are firing the projectile from a height of 0 feet, which is not true. The design of a catapult requires that the projectile be launched from a height well above ground level. Moreover, the projectile hits the ground at 400 feet away. This is not even close to making it to the castle wall. It'll likely crush our soldiers. So let's go ahead and try this again, and in the process, use some different prerequisite skills. Suppose someone modified the function to be the following. Now when does the projectile hit the ground? Go ahead and pause the video, attempt this on your own, and be sure to sketch a graph of the resultant path of the projectile. Just as in our first try, you need to be able to interpret what hitting the ground means mathematically in terms of our function. Again, this just implies we need to solve h of d is equal to 0. Second, we solve this equation. Doing so requires either factoring and the zero factor property, or the use of the quadratic formula. Truthfully, I wouldn't use factoring here, even though I show the process right now. The only reason I was able to quickly find the factorization is because I built this problem. If someone handed this problem to me, I would spend maybe 10 seconds trying to factor, call that good, and move on to the quadratic formula. That being said, you should almost always try factoring first, because if it works, it's usually faster and cleaner. The third prerequisite skill that we're using here is the same one that we did in our first try. We sketched this parabolic path. Again, I am not concerned about the vertex here because, well, there's still going to be issues. We can see that the projectile is at ground level at negative 30 feet, which is 30 feet behind us, and then 530 feet from the catapult.
Time for a reality check.
Now, is this realistic, and is this what we want? Our issues in the first try were that the projectile was being fired from the ground, and it was not going to reach the castle wall. In this case, using our prereq skills, we can determine that the initial firing height of the projectile is 15.9 feet. That could be realistic. So it seems like we fixed that issue for now. What about the distance the projectile flies? According to our model, the projectile is at the ground level at negative 30 feet and then 530 feet from the catapult. In this case, the projectile might hit the wall, but we didn't actually mention the height of the wall. What if we were aiming at a battlement 30 feet above the ground that's sitting on top of the castle wall? When you evaluate our function at 500, we get an output of 15.9 or 15.9 feet. And this is not high enough to hit that battlement. So let's go for another try. In the previous two examples, we relied on someone handing us a function that would hopefully work for this situation. I think it's time to take things into our own hands and build our own model. Let's pretend that the engineers for the catapult let us know that for the projectiles we're firing at the castle walls, the maximum horizontal distance we can get is 600 feet. Thus, the projectile should hit the ground when d is equal to 600. Let's also make a hybrid of the previous example by assuming that our other root for this function occurs when d is equal to a negative 30. Finally, let's suppose we have someone with a spyglass who estimates that the battlement on top of the castle wall is 30 feet above ground level. Remember, we want to hit that battlement, and the castle wall is 500 feet away, so this means we need the projectile to be at a height of 30 feet when it is 500 feet away. Going back to our prerequisite knowledge, we know that 2 points will create a line, but we need 3 points in general to uniquely describe a parabola. Luckily, that's what we've been given here. So, using this information, what is our function for the quadratic model? Again, pause the video and take some time to build a quadratic model. This can be done in two different ways, but I'm going to use the easiest, which will take advantage of our prerequisite knowledge of how zeros of a quadratic function are related to the graph of the function. Doing so leads to our quadratic model having the form h of d is equal to a times d plus 30 times d minus 600. The only other prerequisite skill used in this try is the knowledge that any point on the graph of a quadratic must also satisfy the equation of the quadratic. Hence, our model is as follows. Despite this being a capstone video and me not wanting to review within a capstone video, I want to take a moment to state that this is a perfectly fine form in which to leave your quadratic model. However, some of you might have instructors who force the final form to be in what's called general form, and that is the form that's completely distributed without any parentheses. But the only thing this extra work really gives us is an easy way to refer to the vertical intercept of the model. That is, if someone asked us, what height is the projectile initially fired from with this new model, we could quickly respond with 10.2 feet.
Time for a reality check.
Is this realistic? Well, like the previous try, that second try, we now have a forced starting height that might be correct, depending on the design of the catapult. However, everything else is falling into place. This is the most realistic of all the tries so far. Let's force the last bit of realism here. Suppose the engineers designed the catapult so that our projectile gets launched from a height of 20 feet. In all previous tries, we didn't really take into account the actual design of the catapult, so we were kind of working on faith in hopes that our model would somehow fit the catapult. Let's also continue to assume that we want to hit the battlement on the castle wall, which is, like we said before, 30 feet off the ground and 500 feet away. Finally, the engineers created this catapult to be powerful enough that we know it can launch a projectile at the wall. But they didn't quite give us an estimate for the farthest it can fire that projectile. That is, we don't know when the projectile will hit the ground again. Now, if I stopped here, this means that we'd only have 2 points, 0,20 and 500,30. However, we know that unless one of those points is the vertex, we need a third point to uniquely define this parabola. Well, it turns out this castle is very well defended, and they have tall pine trees that we have to fire over to hit those battlements. Let's say that we must clear a 50-foot tall pine tree that is 100 feet away from the castle wall. Hence, we need our projectile to be at least 50 feet above the ground when it is 100 feet from the castle wall, which, by the way, is 400 feet from the catapult. You could get cautious and say that you want the projectile to clear 60 feet at that 400 mark. So let's go ahead and use that as our third and final point, 400,60. Now, using this information, build a quadratic model. Go ahead and pause the video and build your model. First, we must recall that given 3 points on a parabola, none of which are the vertex, we can determine the related quadratic function by building and solving a 3x3 system of linear equations. Second, to build such a system, you must recognize that points on a parabola represent solutions to the associated quadratic function. Third, and finally, you must be able to actually solve a 3x3 system. Engaging with all of these prereq skills, we get the following model.
Time for a reality check.
Now, is this realistic? Yes, this is the most realistic for our situation without considering air resistance, wind, and some other advanced concepts from calculus and beyond. However, just to add some functional analysis concepts, let's talk about the lack of domain restriction. This is me kind of being nitpicky at this point, but I like to sneak in these little subtopics of mathematics to make sure you're well prepared. As you can see from the graph of the model, there are some heights that are just not realistic. The projectile will never go below the ground, so we should restrict the domain of our model to limit it to reality. Therefore, using our prerequisite skills with functions and domain, along with finding roots to our quadratic model, we finalize our domain-restricted quadratic model to be the following. While we've successfully built an appropriate model, I would not be covering everything you need for a capstone if I didn't mention one slightly unrealistic possibility. What if someone said you needed the apex of the projectile's flight to be at, say, a height of 80 feet, and that it was to occur 275 feet away from you? And by apex, I really mean vertex. You may also assume that the catapult launches its projectile from a height of 20 feet. Using this information, build a quadratic model. Go ahead and pause the video to figure out the quadratic model. This example takes advantage of a form that students are often forced to place quadratic models into. It's called vertex form. As likely mentioned by your previous instructor, this can be an extremely powerful and useful form for a quadratic, but it often gets over-accentuated in math classes as the ultimate form. In truth, it is rare that you can use it. When you can use it, however, wow, it makes work easy. Let's look at the prereq skills being used here. First, we need to be able to recognize what a vertex is. This is just a simple critical thinking skill, but without the ability to understand that we were given a vertex, you can't go anywhere with this problem. Second, we need to know and understand the vertex form of a quadratic. Third, just as in several of our previous tries, we require the knowledge that any point on the graph of the quadratic must also satisfy the equation of the quadratic. Using these three prerequisite skills, along with basic knowledge of how to solve equations, we arrive at the following model.
Time for a reality check.
Is this realistic? Probably not. It's very unlikely that someone would state, we built this catapult so it launches to a maximum height of 80 feet when the projectile is 275 feet away. Moreover, when we plug in 500 to the function, we get an output of 39.8 feet. So the projectile would fly over the battlement or maybe just hit the tippy top of the battlement. Our best model was actually achieved on our fourth try. Let's go back to our best model. If the projectile follows this trajectory, where is the vertex? Go ahead and pause the video and determine the vertex. There are actually a few ways to do this, and to be honest, I think most people use a shortcut method involving negative b over 2a. However, if you've watched any of my videos involving graphs of quadratics, you know that I appreciate a more concrete and common sense understanding of graphs of quadratics. Whichever prerequisite method you use, you should be able to quickly determine that the vertex is at 262.5, 75.125. Thus, the maximum height of the projectile occurs at 262.5 feet away from the catapult and is roughly at a height of 75 feet. Again, using our best model, determine when the projectile is over 50 feet in the air. Go ahead and pause the video and stretch your quadratic inequality wings to figure out when this happens. As I alluded to, the prerequisite skill used here is solving quadratic inequalities. There are a few sub-prerequisite skills that come into play as well. First, we must recognize that this is a quadratic inequality problem. Then we need to recall how to solve a quadratic inequality. There are a couple ways to do this, and as you can see, I use the graphical method rather than the sign chart method, but either will work. Finally, we need to be able to interpret the results of our solution in both interval notation and verbal form. In this case, the projectile is above 50 feet in height from roughly the 85.3 foot mark to the 439.7 foot mark. In interval notation, you can see right here, it's just this parenthetical notation, 85.3 to 439.7. All previous questions have centered on topics common to all Algebra 2 or intermediate algebra courses. The following topic is usually covered in a college-level Algebra 2 course, but not always. It's fun to challenge yourself to see if you can do it, but don't be too discouraged if you've never seen it. Suppose we have our standard catapult that we've been using, with projectile path given by the following function. But now let's include another catapult, located 10 feet behind us, which fires off a projectile along the path given by the second function. Now, the second catapult is designed to strike the barracks within the castle wall. Is there a possibility that the projectiles fired from these catapults will collide in midair? And if so, where is or are the possible points where the projectiles could collide? Go ahead and pause the video, give yourself some time to ponder this question, and try your best to figure out how to answer this. What we have here is actually a system of nonlinear equations. Each equation represents the height of a projectile, and we want to know, will these projectiles ever share the same height? Well, luckily, they both share the same output variable, h, so we can set these two functions equal to one another using substitution. Now you can see you have an equation that only contains one variable, d. What I'm doing here is I'm collecting like terms. So basically, I'm collecting the coefficients of d squared together, the coefficients of d together, and the constants together. Because what I'm going to do from there is save those as variables in an online graphing utility or an online computational utility. This is much cleaner than multiplying both sides by the LCD to clear fractions and leads to the same results. It's also great to see how to use technology in these types of problems, but remember, you shouldn't use technology as a crutch. But it is totally understandable to jump to technology if you have problems that involve ugly numbers like this. In the end, we see these projectiles have a chance to collide at roughly 53 feet and 472 feet from the catapult.
Time for a reality check.
Now, is this realistic? This is an interesting question. A lot of people would look at the graph and think that this means the projectiles will meet. However, that's only true if they were fired in line with one another and at such a time interval that it could be possible for them to collide. The missing dimension we don't see here is time. For example, we could fire off our catapult at noon and the newer one at 3 p.m. In that case, there would never be an issue. Applications are a tricky topic because I know some instructors who avoid them like the plague, and others, myself included, who build an entire course around them. The reality is that mathematics, especially for the citizen and not the mathematician, is meant to be applied. Suppose you're in the business of selling gears for these catapults, and you know that you can sell 32 gears at 20 gold coins each. But for every 1 gold coin that you raise the price, you sell 2 fewer gears. What's the optimal price that you should charge in order to maximize your revenue? The main prerequisite here is actually not quadratics, but instead a knowledge of revenue. You must remember from your prerequisite math courses way long ago that revenue is the product of the selling price and the number of items sold. In this case, we know that we sell 32 gears at 20 gold coins each, but we're going to adjust that. We're actually going to charge 20 plus C, where C is the number of additional single coin price increases. However, we know that we are not going to sell as many if we raise the price. The number we sell is 32 minus 2C. In other words, if C is equal to 1, well, we sell 32 minus 2 or 30 of these. If C is equal to 10, well, we sell 32 minus 2 times 10 or 20. 32 minus 20 is 12, so we only sell 12 of these things. This is our revenue function. The first factor represents our new price. The second factor represents how many we're going to sell. Notice that this is a quadratic function. Our prerequisite graphing skills tell us that the horizontal intercepts occur at -20 and +16, and that halfway between is the vertex of the graph of this quadratic model, which occurs at c equals -2. Additionally, we know that, again from our prerequisite material, the parabola will be opening downward because the lead coefficient is negative, if we had bothered multiplying it out. Hence, we have a maximum at c equals -2, and its value is 648. That is, we would maximize our revenue if we charged 2 gold coins less, and the revenue we would get is 648 gold coins. The moral of the story is that we should charge 18 gold coins for these gears rather than 20. Thank you for watching this capstone review video on quadratics. As always, this content should be prerequisite to the course in which you're currently enrolled. If you found this material unfamiliar or if it was confusing to you, then I recommend you click on the provided relevant prerequisite links listed below for further help. However, if you find you're continually doing this, you might want to consider speaking with your instructor about other course options. On that note, I sincerely hope these videos help you achieve success in your transfer level math and science courses. Cue the music.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.